All right, cool. So hi, this is Baron Curtin and Heather Geiger. We will be presenting Project 1. So for this project, we continued with our analysis from assignment 1 of the Facebook ego node data from the Stanford dataset collection. Just for a little summary, took over the files. There are edges files, which have two columns, node IDs in both columns. The circles file, each line will have an ID column followed by anywhere from 1 to 100 additional columns. The circles represent groups of users, and each node ID in every field of line is connected to the ego node. We have the feature names, which gives information on the column names for the features that are in the ego feet and feet files. And the feature names include stuff like gender, education, class, etc. So starting off, we imported all our necessary libraries, some additional Jupyter notebooks set up, Matplotlib, Seaborn, NumPy, Pandas, SciPy, Pathlib, and ITER tools. So to parse the data, created a bunch of helper functions that would parse each file based on the idiosyncrasies that occur in every file. So there's a separate function for the circles file, edges, ego feet, and feet names. Each one does a different thing according to the file. Those are all loaded into a dictionary so that we can kind of mimic a case function from other programming languages. So, once we got all of the parsed files loaded, we had to get our categorical feature from the feet files. And essentially, the way that feet file was structured was that it had a semicolon to delimit each kind of identifier. We found that the gender one had it said gender and then like anonymous feature 78. And there's actually two lines labeled gender, but we figured since the second one was more often than not 0, that the first one, feature 78, was the more appropriate one for gender. And then we just kind of coded it gender 1 and gender 0 because the Facebook data is anonymized. Yeah. So then we went into the graph construction, similar stuff from last time where we added edges from, used to add edges from, passed a list of values to it from both the circles and edges file, and then we appended the attributes of the gender to each node. Using the set node attributes, what it does is when you print or actually iterate through all of the nodes, you can kind of get all of those different values. So each node will have gender 1, what node number it is, etc. So then plotting the graph, colored by the degree centrality, or between the centrality, size, similar thing. You can see the graph below. You can see that there is one node in the middle that's really large. I believe that's the 0 node. I'm not quite sure from here, but the tables below will definitely tell the story of the graph.
And so in the next section, we measure the degree centrality and eigenvector centrality per node. So we create this data frame where it has for each node the node name, which is just a number, and then the degree centrality for that node, the eigenvector centrality, and then we also have the gender, since we're including that attribute as well. In the data, it's around 60%, 40% for gender 2 versus gender 1. So it makes sense where there's maybe, a slight bias towards 1, but it's close enough where it makes sense that it's likely that one is males and one is females, but we don't know which is which. And then this is just showing the top nodes by degree centrality. And so of those top 10, 9 are gender 2. And then eigenvector centrality, the top nodes are a bit, these are balanced for gender. But that's, we want to look at the overall trend, which we're going to do in the next section, not just the top ones. And this is looking at the top, excluding the ego node, since obviously the networks were set up by definition to have the ego nodes as the most central, so we want to look outside of that. And then looking at the averages, we see that gender 1 has a higher measure of centrality for both degree and eigenvector. And we also see, if you compare mean versus median, that it seems like there's likely to be a right skew, and we plotted it out for degree centrality, and we indeed see that right skew if you visualize it. And then we also ran a t-test for eigenvector centrality, and we found that it's very significant, where it's a very significant difference between the eigenvector centrality for gender 1 versus gender 2, and nodes of gender 1 tend to have a higher centrality score than nodes of gender 2.